Ladies and gentlemen, welcome to the first talk of this session. The speaker is Professor Huy Tuan Pham, who is a well-known expert of probabilities and additive combinatorics. He will talk about additive combinatorics from a combinatorial perspective. Please welcome him.
Thank you for the introduction and for the invitation to this great event. So today I will tell you about several questions in additive combinatorics, but the main surprising message from our approach is that we can tackle these problems very well, even if we forget mostly about the addition and the group structure involved in the problem and move to a much more general combinatorial perspective. But hope by the end, this message will be clearer. So to start, let me introduce one of the most fundamental objects in additive combinatorics, and that's the notion of a sum set. So at the beginning of the talk, let us consider an abelian group G. For a finite subset A of G, we will define the sum set A plus A. This is simply the collection of all elements of the form A plus B, where A and B are elements of A. Now later on in the talk, we'll also see other variants and generalizations of this notion, in particular to non-abelian groups, but I'll tell you as we get there. Now, associated to this notion is a key parameter that we call the doubling, and I'll denote it by Ka. This is simply the ratio between the size of the sum set A plus A and the size of the set A. Now, one of the most fundamental questions in additive combinatorics is the following. What can we say about sets A that has a small doubling, that have doubling Ka bounded above by some parameter K? So to develop some feelings for this question, let's consider one of the most classical setup when G is the group of integers Z. So in this case, it is a simple exercise to show that a set A will have A plus A at least twice the size of A minus 1. Here, equality will occur if and only if A is extremely structured, so if A is an arithmetic progression. On the other hand, it's easy to see that A plus A can have size as large as quadratic in the size of A, and if A has no structure whatsoever, then this upper bound will be closer to being attained. Now, we can ask, beyond this very structured example of an arithmetic progression, are there other integer sets A for which the doubling is still very small, perhaps bounded above by some constant? And indeed, the answer is yes. An important class of examples are given by the so-called generalized arithmetic progression, or GAP, with some bounded dimension D. So here's a formula for a generalized arithmetic progression, but you can ignore it. You can think about a generalized arithmetic progression in dimension D simply as what you have by starting with a box in the D-dimensional lattice ZD, and then take a suitable linear projection to map the D-dimensional box back to the integer axis. Now, if you add a box in D-dimension to itself, then roughly each of the side lengths will at most double, so the volume of the box will grow by at most a factor 2 to the D. And likewise, you can show that a generalized arithmetic progression with in D dimension would have doubling bounded above by some constant depending only on D. So in particular, now towards this question of what are integer sets with doubling bounded above by some constant K, there is a large class of examples which are given by dense subsets of generalized arithmetic progressions with bounded dimension D. We can ask if, other than these obvious choices, are there more complicated sets A that have a small doubling? And a very remarkable theorem of Feynman roughly tells us that the answer is no, at least qualitatively. In particular, Feynman proved that if we have an integer set A with doubling at most K, then A must be a dense subset of a generalized arithmetic progression P whose dimension D is bounded as a function of only the doubling parameter K. Now, Feynman's theorem is a very satisfying answer in a qualitative sense. So for instance, when we fix K as a constant and let the size of the set A grow to infinity, but still quantitative aspects of Feynman's theorem, so in particular, the precise dependence on the parameter K of the dimension D and the density of the set A in this theorem, these are still not fully understood, and they remain to be a fundamental interest in additive combinatorics. Now, without going into too much detail, let me briefly mention that the proof of Feynman's theorem, and in particular the very influential alternative proof by Rouja in the 90s, employs an analytic approach, or use Fourier analysis, together with other influential ideas like the Rouja's modeling and covering lemmas. Now, Feynman's theorem is one of several results that all run along the major theme in additive combinatorics to associate to a set A with small doubling a certain explicit notion of structure. For instance, in the case of Feynman's theorem, we say that A is dense inside some globally structured object. And these statements have a lot of applications across mathematics and computer science, in particular, for example, in random matrix theory, a study of approximate groups, in certain parts of analysis, and in theoretical computer science. On the other hand, they come with certain drawbacks. So often in these explicit structural statements, they come with a weak quantitative dependence on the parameter k, and they will only give us non-trivial information about a set A if the doubling parameter k is fairly small compared to the size of the set A. Now, on the other hand, as soon as the doubling parameter k becomes little o of the size of A, we already expect the set A to have a lot of additive structure. And indeed, there are important applications that we will see later where it is important for us to already capture the additive structure in A as soon as the parameter k becomes non-trivially small. So motivated by these applications, in this talk, we will also see a broader way to quantify the structure of sets with small doubling, and I will roughly categorize these different notions of structure to the following three types. So first we have the explicit structural type, for which Feynman's theorem is an example, and in this in this notion of structure, we want to say that sets A with a small doubling have a certain explicit describable structure. We can also consider structure in a more statistical or enumerative sense. So here we want to show that there are very few sets A which have a small doubling. And finally, we'll consider a probabilistic or complexity theoretic perspective, where we want to say that for sets A with a small doubling, the doubling bounded above by the parameter k, the sum set A plus A can be well approximated by using significantly few bits. In particular, much fewer than the number of bits that we need in order to prescribe the set A. Now, towards these three notions of structure, we'll also see that our approach has one common feature, that is it's overarchingly very combinatorial. So most of the time, in the heavy lifting steps, we will forget completely about the group involved in the problem, and we will move to a general graph theoretic representation of the additive objects that are involved. And also, we'll make heavy use of the probabilistic method. So we use randomness to probe and approximate the structures of the object that we care about. So now this is roughly the plan for the talk. So here I have these three categories of structures, and we'll have roughly one result for each of them. We'll start with a structural result, which is a resolution of a conjecture of Rouge around the structure of sets with small doubling in abelian groups with bounded exponent. And then we'll move to the statistical or enumerative notion of structure, and this is towards application in the study of Ramsey-Cayley graphs. And at the end, we'll discuss the probabilistic perspective through the problem of analyzing the independence number of sparse random Cayley graphs. This problem itself has interesting connections and corollaries for questions in additive combinatorics. Okay, so let me begin with the first part of the talk. This is towards understanding Rouge's conjecture. So Rouge's conjecture is in fact a direct analog of Feynman's theorem, but now for a class of abelian groups that is very different from the group of integers, in particular the abelian groups with bounded exponent. We say that an abelian group G has exponent R if R is the smallest integer such that the order of every group element is a divisor of R. So throughout this discussion, we can just think about the group G as the group Z mod R raised to the power D. So the canonical group of exponent R. Now, for a subset A of an abelian group G, say of bounded exponent R, it's clearly the case that the size of the sum set A plus A is at least the size of A. And in this case, equality can be achieved, for instance, when A is a subgroup of G. Now, in particular, a class of examples that we can give for sets A with doubling bounded above by some constant, let's say K, are in particular dense subsets of subgroups of the group G. Now we can ask if there are more non-trivial examples that are very different from those, and Rouge's theorem says that at least qualitatively, the answer is again no. So in particular, Rouge proves that if we have a group of exponent R, and A have doubling K in the group G, then A must be a dense subset of a subgroup H, for which the size of H is at most the size of A times some constant that depends only on the exponent R and on the doubling constant K.
But like that subset of finite.
Yeah, so I mean, so So here, I mean, when I mention dense, I mean quantitatively. So for instance, this is the notion of dense that I'm referring to. So the density of A inside the subgroup H is a constant that depends only on the parameter K. So if we think about K as being fixed, then this is really an absolute constant. Okay, so that's my notion of being dense. Okay, so, well, but very soon, as in the case of Feynman's theorem, we will be interested in quantifying Rouget's theorem. So in particular, we want to know how this constant CRK depends precisely on the doubling parameter K. Okay, and this is the content of Rouget's conjecture that was posed in the same paper. So in particular, Rouget conjectures that the correct dependence of this constant CRK on the parameter K is of this form, R to the order big O of K. So it's exponential with a linear dependence on K in the exponent. And this conjecture is not there just for no reason. So we can consider a very simple example which tells us that in order for this statement to be true, we will need at least to put in this term roughly something like R to the 2K. Okay, in this example, we can just look at the canonical example of ZR to the D, and we take the set A to consist of 0 and the D coordinate vectors, E1 up to ED. We can check that the doubling of this set will be roughly D over 2, and on the other hand, the smallest subgroup containing the set A will be the whole group G, which have size R to the D. Okay, so the correct dependence here, based on this example, should be at least exponential in K, and Rouget conjecture that this exponential dependence on K should be correct. So now there have been quite a few works towards Rouget's conjecture. In his original paper, Rouget proved that we can replace R to the CK here with roughly a function that is R to the K to the 4. And later in joint work with Ben Green, he improved this dependence to roughly R to the K squared. And in the breakthrough on the quasi-polynomial Bogoliubov Rouget's lemma, as a corollary, Sander proved that we can take the size of H to be at most the size of A times a term that is roughly R to the K times a polylog K factor. So getting very close to the correct linear dependence on K in the exponent. On the other hand, this is the best that we know in a general abelian group of bounded exponent, but there's a special class of abelian groups of bounded exponent that is specifically nice, and that's the class of finite field vector spaces. And over finite field vector spaces, already from 2009, Green and Tao show that Rouget's conjecture holds true. So in particular, they show that over the group F2 to the D, indeed, we can show that the correct that the size of H can be taken to be at most roughly 2 to the 2K times the size of A, which is the correct dependence on K. And this was later sharpened and generalized by Evans-Zohar and Lovett to in particular resolve Rouget's conjecture for all of the finite field vector spaces Fp to the D. Okay, and here we see that indeed the dependence on K, at least in the main term, is roughly P to the 2K, as the example that we saw earlier suggests. Okay, so the techniques in the previous work roughly come in two distinct directions. So first we have the analytic technique, roughly the same way that Feynman's theorem is proved. And this technique has the advantage that it, in general, abelian groups of bounded exponent, but it seems very hard to remove the polylog K factors that remain from the analytic approach. On the other hand, the techniques that work over finite field vector spaces are significantly different. So they are the compression technique that was adapted from extremal combinatorics. And here roughly what we do is to perform a lot of local modifications to reduce the problem to certain explicit structured examples that we can check easily. And in order to get these local modifications to work, we do rely very strongly on the vector space structure. And this technique doesn't give us any result for an abelian group, a general abelian group of bounded exponent. And indeed, there are important cases where groups with exponent divisible by more than 1 prime behave significantly different from a finite field vector space. And they form many important examples in computer science. So it may be not just a technical point that the compression technique doesn't work over general abelian groups of bounded exponent. Okay, so the first result I want to mention is in joint work with Jacob Fox, where we prove Rouget's conjecture in a strong form. So in particular, we show that if we have an abelian group G of exponent R, and A have doubling at most K, then A must be a subset of a subgroup H, whose size is at most the size of A times roughly R to the 2K. Okay, so in particular, Rouget's conjecture hold, and we see that we also recover the correct roughly R to the 2K dependence on K. Okay, so as I alluded to earlier, our proof of Rouget's conjecture is in fact mainly combinatorial. So first I need to tell you a little bit about how we can create a combinatorial setup in order to study the additively combinatorial objects that we have introduced. So, so far we have the additive input, which consists of an abelian group G and a subset A of G with doubling bounded above by K. We can describe the input in a more combinatorial way as follows. We can consider a complete graph whose vertices are identified with the group elements of G. And on this complete graph, we consider a proper edge coloring where the edge between two elements X and Y is colored with the color X plus Y. It is easy to check that this is going to be a proper edge coloring. In fact, if you are careful, you will want to put certain self loops in this edge coloring as well. But for the purpose of this talk, let's safely ignore all of these technical details. Now, a set A in the group G with doubling bounded above by K would correspond to a vertex subset of this complete graph whose induced subgraph receive relatively few colors, receive at most K times the size of A many colors under this specific edge coloring C. Now, it turns out that for many of the additive problems that we will discuss, it is completely safe to ignore the fact that this edge coloring comes from the addition structure on the group G. And just remember the combinatorial input that we have a complete graph equipped with a proper edge coloring. And if we induce this complete graph on the set A, then we get a complete graph on A with a proper edge coloring that uses relatively few colors, at most K times A many colors. So this will be the combinatorial setup that we will work with in this talk. Okay, so now in this combinatorial setup, our main input will be what I call the key combinatorial lemma, which I will try to describe to you now. In all of the three applications that I will discuss in this talk, in fact, this key combinatorial lemma will appear and play some important role. So first, let me introduce a piece of notation. Given an edge coloring of a complete graph, for two vertex subsets A and B, let me denote by n of AB the set of colors that appear in the edges that go between the vertex sets A and B. Okay, so now I will state the key combinatorial lemma, and the statement is a bit long, but just follow along with me in the figure. It's much easier to remember what the lemma is doing in a figurative way. Okay, so let me go over this statement slowly. So in the setup, we have exactly the setup that we have considered earlier. We have a proper edge coloring on a set of vertices A of size little n, and this proper edge coloring uses relatively few colors, at most K times n many colors. There's a small technical condition that you can ignore, which we want to say that each color appears not too many times, so roughly big O of n over K many times, but this condition can be safely ignored in most of the applications. Now, the conclusion of the lemma is that we can find a small set of colors S, a set S of size at most big O of K, and in many cases we can even make this little o of K, such that the set S will now partition our vertex set A into a few balls Bi that satisfy three key conditions. So let me tell you about these three key properties. The first property is very simple. We want the balls Bi to cover a significant proportion of the vertices in the set A. So let's say at least half of the vertices in A are contained in these balls Bi. The second property is that each of the ball Bi can be connected using only the colors in the small set of colors S. And the last and the most important condition is that for any of the balls Bi, no matter which subset A prime of A that you pick, as long as A prime is not too small, so as long as A prime is at least some constant fraction of vertices in the graph, the set of colors between Bi and A prime will have size at least some universal constant factor times the total number of colors that we have in the picture, which is K times n. So roughly, this last property tells us that these balls Bi that we have constructed are very well expanding sets. They are very well expanding and very well connecting with respect to any not too small part of the graph. So that will be very useful for us to learn global information about the structure of the set A once we have these expanding balls Bi. Furthermore, the second property tells us that there's a single small set of colors S which simultaneously connects up all of these balls Bi that lie all over the graph. So in particular, the set S will allow us to produce some sort of global structure among these balls Bi. Okay, and we'll see later on in the applications how these two properties will be useful to us. Okay, any questions about the statement of the lemma? Rather, we should just remember what the picture is saying. Okay, if not, then let me briefly tell you how we can use the combinatorial lemma to at least get a sketch of proof for Rouget's conjecture. So in the first step, we translate Rouget's conjecture from the additive setting to the combinatorial setting by constructing the edge coloring that I have told you before. Then we apply the key combinatorial lemma, which produces to us these very well expanding balls Bi. Now, after we have this picture from the combinatorial lemma, let's go back to the group theoretic setup. So in the second step, let's remember that each of the colors in our graph actually correspond to a group element. So in particular, the set of colors S now correspond to a set of elements of the group, and I can let H be the subgroup that is spanned by the colors in the set S. After this, roughly what we will show is that if we quotient the set A by this subgroup H produced by the colors in S, then we will get a set A mod H that behaves like a set with doubling bounded above by a universal constant instead of K. So originally we have a set A for which A plus A is at most Ka, and now we have produced a set A mod H for which the doubling of A mod H is a universal constant that is independent of K. So I'm hiding here some technical, very small dependence on K, but we can just safely ignore this for this discussion. So very briefly, let me tell you how we bootstrap the doubling from K to a constant by using the key combinatorial lemma. So roughly, the third property in the combinatorial lemma would tell us the following. If we look at the partition into H cosets, which now partition our set A into a bunch of sets like this, then if we take a coset of H with non-empty intersection with A, in particular it contains one of the balls Bi, then the sum set of the part of A inside this coset and any large constant fraction of A will be at least some universal constant times K times N, where N is the size of A. You can use this fact together with some additional additive combinatorial idea to show that if A mod H have doubling lambda, then you can go back to the set A and show that A plus A must have doubling. A must have doubling at least some constant times lambda times K. So we regain the factor of K, and that immediately forces lambda to be bounded above by a constant because A have doubling at most K. Yeah, one needs a little bit more ideas in order to execute this argument, but really the heavy lifting step is done by the key combinatorial lemma. And once we are at this conclusion, then finishing the proof is very easy because now A mod H is a set that has doubling roughly bounded above by a universal constant, so we can apply any qualitative version of Rouget's theorem that we want, and then still collect up all of the missing elements that we ignored in the previous step to show that A must be contained in a subgroup H with size at most A times roughly exponential in K. Okay, so here this argument will not really produce a sharp constant 2 in front of K, but we can input a few more additional ingredients to recover the sharp version that I claimed earlier. Okay, so this is the first application of the key combinatorial lemma. Next, I will discuss a second application of the key combinatorial lemma, and this time this will be towards the study of random Cayley graphs and Ramsey Cayley graphs. So first, let me introduce a convenient term from Ramsey theory. Given a graph on n vertices, we'll say that this graph is C Ramsey if it has no clique or independent set of size bigger than C times log base 2 of n. So in Ramsey's theory, one of the central questions is to, in particular, construct graphs on a large big N number of vertices for which the clique and independence number is very small, bounded above by C log n, for instance. And in this direction, of course, we have the very remarkable theorem of Additive, going back all the way to 1947, where he shows that, in fact, almost all graphs on big N vertices are 2 Ramsey. And this theorem is very remarkable. It's one of the first applications of the probabilistic method, and also its proof is surprisingly simple. So all that we need to do is to consider an Additive random graph Gn1/2, or in other words, a uniformly random graph among all of the graphs on big N vertices. Then we consider the first moment or expected value for the number of clicks or independent sets of this specific size 2 times log base 2 of n, check that this number is very small, and then immediately conclude that almost all graphs do not have any click or independent set of size 2 log n. Now, despite being very simple, it's been almost 80 years, and we do not have any significant improvement over this simple argument of Additive in 1947. And in fact, an outstanding open problem is to explicitly construct, either in the mathematics or the computer science sense, a C-Ramsey graph for some constant C, not necessarily 2. So in this talk, we'll not be constructing an explicit C-Ramsey graph, but instead, we'll try to consider a different example of random graph that uses significantly fewer bits of randomness than the example of Additive random graph G and 1/2. So in particular, we want to find a collection, a random graph with a significantly smaller support, which already allow us to construct good Ramsey graph. And that's one of the motivations for us to consider Cayley graphs and random Cayley graphs. So in this talk, when I mention a Cayley graph, I will fix a finite group G. And given this group G and a symmetric subset S of G, so this just means that whenever G is an element of S, G inverse also has to be an element of S. We can then construct the Cayley graph with generating set S. This will have vertex set G, and we connect 2 elements X and Y if X times Y inverse is an element of the generating set S. Now, given this definition, we can construct a natural distribution on the Cayley graphs of G. In particular, given a probability parameter P, we consider the random Cayley graph GP as the Cayley graph with a random generating set S, where each equivalence class, GG inverse, is included in S independently with probability P. Okay. So, as I mentioned earlier, one of the motivations for us to look at the random Cayley graphs from the Ramsey theoretic perspective is to construct a Ramsey graph using fewer random bits than the Additive random graph. Also, it turns out that in a very few explicit small Ramsey graphs that we know, they all turn out to be Cayley graphs. In fact, an even more special type is a Paley graph. Now, I will not define a Paley graph for this talk, but studying Paley graph is a question that has attracted a lot of interest in both combinatorics and number theory, and it seems to be a very challenging number theoretic question. So for us, understanding first the properties of random Cayley graphs is also perhaps a proxy towards better understanding the properties of Paley graphs. Now, beyond Ramsey theoretic motivations, random Cayley graph and Cayley graphs are extensively studied across mathematics and computer science, have applications to quantum coding theory and spectrograph theory and so on. Okay, now for us today, we are specifically interested in Ramsey properties of random Cayley graphs. So let me, for this section, fix the sampling probability P to be equal to 1/2. So G1/2 is really a uniformly random Cayley graph among all Cayley graphs of the group G. And our goal will be to study the independence number of this random graph G1/2. Let me note that in this example, the distribution of the click number and the independence number are exactly identical. So everything we prove for the independence number will also apply to the click number, and therefore will obtain the Ramsey property that we want. Okay, and one of the explicit motivation for our discussion will be the following beautiful conjecture of Alon, where he conjectured that there is some absolute constant C, so that every finite group admits a Cayley graph that is C-Ramsey. Okay, so first, well, it seems that I have been a little bit going on a digression because we started with sets with small doubling, and so far I haven't really stated any explicit connections between Ramsey properties of random Cayley graphs and additive combinatorics. So let me now make that connection. So in this case, when we are working with a general group, not necessarily abelian, let me define for a subset A of G, the product set A times A inverse. This is a collection of all elements of the form A times B inverse, where A and B are elements of A. So if you specialize to an abelian setup, then I'll switch to the additive notation, and then of course this product set AA inverse will simply become the difference set A minus A, which of course is very closely related to the sum set A plus A that we studied earlier. Now we can observe that A is an independent set in a Cayley graph with generating set S, if and only if this product set A times A inverse, well, subtracting the identity element, is a subset of the complement of the generating set S. And given how we define the random generating set S in a random Cayley graph, we can immediately make the connection between the first moment of the number of independent sets in a random Cayley graph GP and the number of sets with small product sets in a group G. So in particular, the expected number of independent sets of size T in the random Cayley graph GP, you can easily show to be this summation over all subsets of the group of size T of roughly 1 minus P raised to the power, that is the size of the product set A times A inverse, up to a factor of 2. And in particular, we'll see later on that we'll control the first moment of the number of independent sets in a random Cayley graph by, indeed, bounding the number of sets with small product sets, which is pretty much an additive combinatorial question. Before getting there, let me mention some of the results that we know earlier regarding the Ramsey properties of a uniformly random Cayley graph. But first, we have a beautiful theorem of Alon from the 90s, where he showed that in a general group G, the independence number of a uniformly random Cayley graph is at most of order log n squared, where n is the size of the group with high probability. So in particular, we are just off from the Ramsey property by this quadratic factor here. Now, up to our work, Alon's theorem is still the best result that we know inside a general group G, and the only more precise results are over specifically nice abelian groups. So in particular, there's a result of Ben Green, later sharpened by Green and Morris, where they show that if we look at the prime cyclic group Z mod n, then the independence number of a uniformly random Cayley graph will be asymptotically 2 plus 0 of 1 times log base 2 of n with high probability. And what's remarkable is that this number is in fact asymptotically the same as the independence number of an Edish-Renyi random graph, Gn 1/2. And the only other more precise result that we know is in the setup of a finite field vector space Fp to the d for fixed p and d large. So in this case, Green, and then later sharpened by Marzovic, show that the independence number will be in fact of order log n with high probability, where n is the size of the group, so p to the d. So already we see that in these very simple and nice abelian groups, a uniformly random Cayley graph will fail to be Ramsey by this log n factor. We'll come back to this point a bit later. Okay, so in joint work with David Conlon, Jacob Fox, and Liana Yepremian, we show that in fact in an arbitrary group G, not necessarily abelian, the independence number of a uniformly random Cayley graph is of order at most big O log n with high probability. So in particular, this result is sharp unless we make further assumptions on the group G, and it's sharp by considering simply the finite field vector spaces Fp to the d. And as I mentioned earlier, we proved this theorem via the connection to counting the number of subsets of a general group G that have a small product set A times A inverse. And this is the answer for the number of such sets. And again, this answer is sharp up to the universal constants that are involved in the theorem. So of course, based on this second theorem, we can see that this theorem is really a statement about, that is saying that sets A with a small product set A times A inverse are structured in a statistical or enumerative sense. And also, again, this statement is purely group theoretic, an additive combinatorial, there's no randomness in it. But yet again, we'll see that our proof of this statement will rely on the key combinatorial lemma. And again, it takes place in an entirely combinatorial setup. So for the second time, let me tell you how to go to the combinatorial setup and connect with the discussion of random Cayley graphs and number of subsets of the group with a small product set. This will be very similar to the discussion that we had before. So again, we consider a complete graph where the vertices are identified with the group elements, and now we can consider the following edge coloring. We assign to an edge between two elements x and y the coloring given by the equivalence class, xy inverse, yx inverse. You can easily check that in this edge coloring, each color class will be either 1 or 2 regular. So each color class will have bounded degree. So here are two examples of what the edge coloring looks like in the group Z2 cross Z2 and the group Z mod 5. Now, in this more combinatorial description, a set A of size n with small product set A times A inverse will simply correspond to, again, a vertex subset that induces relatively few colors in this specific edge coloring. And a Cayley graph will simply be the edge union of some of the color classes in this edge coloring, and likewise, a random Cayley graph is simply the random union of some of the color classes. So again, for the second time, it comes a surprise. It turns out that we can completely forget about the fact that this edge coloring comes from the specific group structure, and just remember the combinatorial constraint that the edge coloring have color classes of bounded degree. So this naturally leads us to studying a generalization of the ensemble of random Cayley graphs. So in this generalization, let me consider a complete graph, and you can specify an arbitrary edge coloring C of this complete graph, where the only constraint is that each of the color class have degree at most delta. Now we'll define an entangled graph, it's an analog of a Cayley graph in this generalized setup, as the edge union of some of the color classes, and a random entangled graph can be defined as the edge union where each color class is included independently with probability P. Okay, so in particular, this model would generalize the Additive random graphs, the random Cayley graph, as well as several other models of random graphs that have been considered previously in the literature, but let me not go into the details here. In fact, in the later work, we generalize vastly the random entangled graph to the example of delta-independent random graphs, but let me not go into that details here. So now it turns out that both of the theorems that I stated before, so the first one regarding the count of subsets of a group G that have a small product set A times A inverse, and the second one regarding the clique and independence number in a uniformly random Cayley graph, both of these results already hold true at this general level of the delta bounded edge coloring on the complete graph and the random entangled graph. So you can see that both of these statements are in fact identical to the statements that we have earlier in the group theoretic setup, perhaps apart from this constant delta that appear in the statement. Okay, so in particular, we resolve some conjectures of Christophidis and Markstrom on the clique and independence number of random Latin square graphs, which are some generalization of random Cayley graphs. So let me tell you a little bit about how we prove this key counting statement. So in this statement, we want to count, we are given an arbitrary edge coloring for which each color class have maximum degree bounded by delta, and we want to count the number of vertex subsets of size little n that induces relatively few colors, at most k times n many colors. And it turns out that the main step towards proving this theorem is the following structural lemma about vertex sets that equipped with a proper edge coloring using few colors. So in this statement, we have a vertex set of size n, and on the complete graph on this vertex set, we are given a proper edge coloring that uses at most k times n many colors. The conclusion is that we can find a tree that covers almost all of the vertices in this set, and yet this tree uses relatively few colors, at most k plus log n many colors, which is a tight answer here. And once we have this lemma, proving the counting result is fairly easy. So roughly, we will start by counting this tree on few colors as the frame for the set of vertices that induces few colors. And after that, we can collect all of the remaining vertices in the set in a quite simple way. So the structural lemma is really the key input to this counting result. And in turn, the proof of this lemma will rely heavily on the key combinatorial lemma that we have seen earlier. Okay, so now let me briefly tell you how we can apply the key combinatorial lemma to prove this structural lemma. So again, we have the key combinatorial lemma, and let's just remember this picture here. We have the small set of colors S, and these bonds Bi, all of them are connected by the colors in S. Furthermore, we have this expansion property. So each of the Bi sees the rest of the graph in many, many colors. Now the set S uses only so far big O of k many colors. So starting from this picture, now what we can do is in log n many steps, in every step we just uniformly at random expose a color in this graph. Okay? Because of the expansion property, the third bullet point here, for every random color that we expose, each bond Bi will connect with another bond with at least some constant probability. So in particular, we can show that at least in expected value, as we expose a random color, the number of connected components in this picture should decrease by some constant factor that is smaller than 1. So in particular, in log n many iterations, we will be able to connect up all of these bonds to form a giant component in this graph. Okay, that would give the structural lemma that we want here. Any questions regarding the discussion so far? All right. So with that, we very briefly just mention one of the last mysteries here, which is that, well, while Alon's conjecture that every finite group has a Cayley graph, we saw that even for very simple groups, the uniformly random Cayley graph may fail to be Ramsey by this log-log-n factor. So it turns out that at least in most of the cases, we can fix this issue by modifying the ensemble of random Cayley graphs to remove certain problematic large independent sets. And so in particular in our work, we also proved that for almost all n, all abelian groups of order n will have a Cayley graph, which is C Ramsey for constant C. So we resolve Alon's conjecture for almost all abelian groups. So for the sake of time, let me not go into the details of this proof. And instead, let me go to the last section of the talk, which will be on certain probabilistic perspective on random Cayley graphs. And our motivation here will be towards understanding the independence number of sparse random Cayley graphs. So in this last part of the talk, we'll be in the sparse regime. So we'll think about the parameter p as a function of the size of the group n that goes to 0 as n tends to infinity. And because this problem is challenging, we'll now just focus on the specific case where G is abelian. In fact, you can just think about a cyclic group from now to the end of the talk. So the key challenge in analyzing sparse random Cayley graphs is that the naive first moment that we have written down earlier, so the expected number of independent sets of size t in the sparse random Cayley graph GP, which we had a formula before, turns out that this will always be too large, no matter how slow p tends to 0. So in particular, let's take the cyclic group Z mod n. We can easily show that there is a large exponential in T, many sets A of size T with doubling at most 10. And just the contribution from these sets to the first moment will give us a contribution that is very large, much, much bigger than 1. So it seems that the first moment method goes into a severe issue here, but we do have some lessons that we have recently in probabilistic combinatorics where we know that the first moment method should be quite powerful. In particular, the first moment, we know, is the main driving force in the emergence of structure in very general setups. And the Khan-Calaye conjecture that I resolved earlier with Jin-Yong Park indeed shows that the first moment functions should always closely predict when structures start to appear in random discrete systems. There are also very nice and intriguing connections to high-dimensional geometry and probability, but I'll not go into that tangent now. Instead, what we will focus on is that the Khan-Calaye conjecture only gives us half of the picture. So it only builds a bridge between the probabilistic threshold phenomena and the union bound obstructions, or the first moment obstructions. On the other hand, understanding these first moment obstructions can be a highly challenging task, and in particular, over the ensemble of random Cayley graph, where we have a lot of structure independency, this is a really challenging task. We saw that we spent almost the entire previous section in just analyzing the naive first moment for the number of independent sets in a uniformly random Cayley graph. But still, we can try to adopt this general perspective and fix the failure of the naive first moment that we considered earlier. So in particular, let me describe to you what is the first moment obstruction that we should search for. So for us, we have a collection H of subsets that we are interested in. And really, in our discussion today, this will be simply the collection of different sets A minus A over subsets A of size T in the group. So given this collection of target structures H, a first moment obstruction is described by a cover C, which is another collection of subsets of the group, so that every set from H contains as a subset some set from the cover C. And the second property that we will want is that this cover C have a small cost, where the cost is simply this union bound proxy, the sum over 1 minus p raised to the size of C. So in particular, our goal in improving the naive first moment is to find a small collection C which covers all of the different sets A minus A and which have a small union bound proxy. Okay, so early before our work, we have the beautiful result of Alon, which shows that the independence number of a random Cayley graph GP is bounded above by roughly p to the minus 2 with high probability. And in fact, his proof can be thought of as a simple construction of a small cover for the collection of different sets A minus A. What do we expect to be the correct answer? Alon conjecture that the independence number is with high probability, roughly p to the minus 1. And the motto here is that a random Cayley graph GP should behave fairly similar to a random regular graph of the same degree, p times n. So in upcoming work with Noga alone, we proved that the independence number of a random Cayley graph GP is with high probability at most roughly p to the minus 3 half. So it's the first improvement in the exponent since Noga's work. And our proof is really by producing a small cover for the collection of different sets A minus A. And let me say that the main challenge here is really in the case where the doubling of the set A is really small, let's say about a constant. And indeed, even just in this setup, we have a question of Lovett, which was open until our work, where let's say over F2 to the D, he wants to construct a small collection of sets. Each of them is a big set, so that it covers the collection of different sets A minus A for on dense subsets A of the group F2 to the D. Of course, if A is dense, then its doubling is automatically a bounded constant. And so even just in this special case, this is the content of the question of Lovett. So our main result, our main technical result is a so-called efficient covering lemma. So here we construct a small collection of sets C. Each of them have a large size, and for which this collection of sets C forms a cover for the collection of different sets A minus A, where the doubling of A is roughly of order K. Okay, so roughly you can think about this statement as telling us that some set of sets with small doubling, okay, so the analogous statement also holds when you replace the difference by the sum. It tells us that some set of sets with small doubling can be efficiently encoded indeed by using significantly fewer bits. And the case K is a constant, resolve in the positive the question of Lovett. And roughly by using this input, together with the first moment obstruction that we mentioned earlier, we can recover the upper bound on the independence number that we stated. Okay, we're not going into the details of this proof, but roughly the main idea behind our proof of the efficient covering lemma is to use various probabilistic approximation of the level sets of the self-convolution A coming with A. And this itself, in combination with the key combinatorial lemma, have a few more interesting applications, but for the sake of time, let me not go into the details here. Instead, let me conclude. So throughout this talk, what we have seen is a combinatorial and probabilistic approach to study sets with small doubling. Roughly, the recipe consists of two steps. We'll first apply the key combinatorial lemma to find these very nice expanding structures in sets with small doubling. And using this expansion structure, we can then refine them to get very good information about the probable structure of the set, the refinement step. And this is really, in some sense, a very different perspective than classical arguments in additive combinatorics, because instead of zooming in on explicit structures, we try to go in the opposite direction. So we try to find a template that is as random-like as possible, and then recover the structure by using this template. And I didn't say much about the details, but our proof of the combinatorial lemma indeed uses a lot of strength of randomness. In particular, we use an intricate random exploration process. And this approach is applicable because it's fairly general. It doesn't require any specific property of the group, and it provides us also with robust structural results in additive combinatorics. And perhaps it brings up the question of, okay, we can re-examine lots of the important structural results in additive combinatorics that we have, for example, Feynman's theorem, and perhaps for many of these statements, already they hold true at a much more general combinatorial level. And if that's the case, then we can have a lot more leverage and tools to tackle important questions in this direction. Let me just end by saying that there are lots of interesting questions to study from here. So for instance, to develop a theory in analog with random graph theory for thresholds in the ensemble of random Cayley graphs or other ensemble of random graphs with significant dependency. And also, Alon's conjecture is open. And to us, we think that really one of the most interesting cases is just over the very nice group F2 to the D, over the Boolean hypercube. Let me end here. Thank you.
Hi, thank you for the great talk. Is there any hope of applying your ideas in the non-tonsure case?
Oh, that's a great question. So indeed, for instance, in our proof of Rouget's conjecture, the heavy lifting step, the combinatorial step, makes no use of the bounded torsion assumption, and we only use the bounded torsion in the refinement step in order to easily take out this convenient subspace H that is spanned by the elements, spanned by the colors in the combinatorial lemma. It seems really wasteful. We've been trying to think whether we can avoid that wasteful step and and make a version of that theorem work even over setups where we don't have the torsion. Or in particular, for instance, we have the still open polynomial Feynman-Rogers conjecture over torsion-free groups.
Yeah, but even recovering results that are already known could be interesting because the method is very different. As you say, it seems to be very flexible.
Right. Yeah. So indeed, yeah, there are quite a few results in additive combinatorics that I didn't go into details where we can recover previously known results. So, for example, robust version of Feynman's lemma, we can recover several of these statements by using this new approach. Yeah, it's a largely new idea, and so I think there's sort of room to explore.
Thank you for great and dynamical talk. And I want to ask about, if you take a random set A, what is the typical size of A plus A set, subset?
So if we take a random set A, then we can, if we want to just understand the size of A plus A, that should not be too complicated. So for instance, for each group element, the probability that that group element is not inside A plus A, that can be explicitly computed, right? Because that group can be represented as the sum of a bunch of disjoint pairs of elements of the group. And if we are taking a random set, we can immediately estimate what is the probability that an element will lie outside A plus A. And based on that, we will get the expected size of A plus A.
So what is the answer?
I guess, yeah, I can work out the answer. Right, so let's say we have a group G of size n, then for a specific element, the group, so it won't be too important, but to avoid certain technicalities that we consider, for instance, a cyclic group, the probability that a group element X is not inside A plus A, where A is a random subset of the group where each element is chosen with probability P, this would be roughly 1 minus P squared raised to the power n over 2, maybe m raised to the power n over 2. And so in particular, the expected size of A plus A will be roughly the size of G minus times 1 minus P squared to the n over 2. And furthermore, we can use standard probabilistic tools to show that the distribution of the size of A plus A will very strongly concentrate around this value, at least in reasonable ranges of the parameter P. And so this will be always roughly the correct size for the sum set A plus A.
Your result that for structural set, it will be constant times size of A, right?
Right, so indeed we will expect...
And the estimate from Wolf is A square, right? Size of A square.
Right.
So I'm asking, would it be A square or it will be...
I see. So well, we do indeed expect that sets with small doubling are very special. So if you take a random set A, the doubling will be really most of the time around order A, at least in reasonable range of parameters again. If you take a small random set A, the doubling will typically be of order A. So the sum set will be roughly of order K, A squared. And that should be the correct answer. Yeah, but really for this, we can get the precise control in most range of parameters.
Thank you.
Okay, let's thank the speaker again.